The next time I see you after today will be after reading week, and it will be for the midterm exam, which will be here in this room. We have 2 hours, but it's not going to take 2 hours, that's for sure. Although you can take as much time as you want. It'll be a mixture of multiple choice, short answer, and long answer. It's going to be 50 multiple choice, and I think it's 3 short answer and 2 long answer. The short answers you can answer with, 1 or 2 sentences, and the long answers are meant to be more like half a page of writing. That's it. Not so bad. There won't be any big surprises, that's for sure. Any questions about the exam? Yeah.
So for the short and the long answer questions, will they be kind of like application based, or like what sort of like types?
Yeah, what sort of questions? Some of them are application based. Some of them give an example of an analysis that was performed and maybe show the output, and then you have to answer some questions about it. Yeah.
Like the code.
Not the code, the output.
Oh, like big,
yeah, so linear regression will be the summary of linear regression, lists all the coefficients and standard the estimate and R-squared and that sort of thing. Yeah, you won't be required to produce any code on the exam. You might be required to recognize some code. Not critical though. And likewise, you won't be required to produce any equations on the exams, but you might be required to identify which is the equation for what thing. Yeah.
So the first 2 weeks of class, we were really kind of diving into the code and introducing us to it. So what part of the material from the first 2 weeks would appear on the midterm?
Yeah, the first 2 weeks, there's not much material on the exams based on the first 2 weeks. Maybe just a small handful of multiple choice questions, I think. So the example question in the exams page, where is it? Yeah, that first one, that's an example of the kind of thing. And there's just a small handful of those, maybe 2 or 3, based on the first 2 weeks. Yeah, the main goal is not to test you on that stuff, it's to test you on the statistical concepts. Other questions? Yeah.
So in the first 2 weeks, when there's like 15 chapters, really don't go in very hard on those chapters?
No.
Okay.
Yeah. The first 2 weeks in the resources for this, I listed a lot of, where are they? Yeah, that's not so bad.
Yeah, the second one. Yeah.
A lot of chapters in that Harvard data science book. You don't need to go and reread all those chapters and learn every little detail about that stuff. That stuff is not the focus of the exam. That stuff is meant to be the focus of the homework. But the focus of the exam really is the conceptual stuff, the lectures and the other readings. Yeah. Yeah, the question is there going to be content from the homework? No, not really. No, I think some of the homework illustrates some of the statistical concepts that we learned about, so those might appear on the exam, but nothing directly from the homework. Yeah. Other questions? Yeah.
Could you just repeat how many short and how many long answers are going to be?
I think it's 3 short answers and 2 long answers. Yeah, that's right. Yes, that's correct. 3 short answers worth 2 points each, and 2 long answers worth 5 points each. So 3 short answers worth 2 each, and 2 long answers worth 5 each, and then the multiple choices are worth 1 each. Yeah. 50. 50. Yeah.
Is there going to be any sort of reviews, slide, or
No, there won't be any sort of review slides. I think the slides at the end of the slides to review. Yeah. Yeah. I am happy to answer questions though. If you have any questions after today, just shoot me an email or talk to me on RTA. Yeah, will I be available for questions over meeting week? Yeah, I will be. Within reason. Yeah, I'm not going anywhere. So if you send me an email, I'll be able to answer it within a day or two. Yeah. Okay, well, like I said, if you have other questions, come and ask at the break or at the end of class or shoot me an email later. So today's material is not on the midterm. So the midterm only covers up to the end of logistic regression. One-way ANOVA, which we're talking about today, is not on the midterm. It will be on the final. The final again is cumulative. It covers everything. But today's material is not on the midterm. And what's more, I think you've seen one-way ANOVA already, right? You saw it last term in 2011. So it should be a little bit of a review, so not quite as heavy as the material was last week. I was looking over the slides again from last week. It was a little bit heavy compared to the rest of the course. Yeah, I acknowledge that. That happens sometimes. So today will be a bit lighter, and it'll be a review, but I'll present it perhaps in a little bit of a different way than you've seen it before, which is always helpful, I think. And it'll set us up for the next couple of topics, which we'll talk about in much the same way. So one of the themes that I want you to get by the end of today is that a one-way ANOVA is just another kind of linear model. And I've said that a couple of times already, but hopefully you'll see how that's true. So let's just start back at a t-test. Remember when you do a t-test, you're comparing two groups. So you randomly sample two groups, and maybe you apply an experimental manipulation to one of them and not the other one. So you might have a control group and a treatment group, maybe they got a drug. And the question you're asking when you do a t-test on those two groups is, it's a bit of a subtle distinction. The question you're asking is not, do those two groups have the same mean? That's not the question you're asking. You don't need a t-test for that. You just compute the mean of controls, 92, and the mean of treatment, 125. You just look at the numbers. Do they have the same mean? No. Those groups do not have the same mean. That's not the question. The question is about the population from which those groups were sampled. So the t-test is asking the question, are those two groups sampled from populations with the same mean or from populations with different means? Or to put it another way, how likely is it that you could have obtained the difference between means in two samples that large if those two groups were actually sampled from the same population? So what's the probability that a difference in means that big could have occurred due to random sampling from the same population? So what's the probability of taking two samples of size 6 from a population, a single population with one mean, and observing a difference in means in their sample that large? That's the probability of observing the data under the null hypothesis. The null hypothesis is, in fact, the population underlying the controls and the population underlying the treatment are the same population. That's a statistician's way of saying the treatment has no effect. If the only difference between these two groups is that these groups received some drug before you took a measurement, and if the drug has no effect, in fact has no effect, then that's like saying these two groups were sampled from the same population. If the drug does have an effect, then that's like saying the treatment group was sampled from a distinct population from the control group, a population whose mean is different than the mean of the control group. So just to recall a sort of basic principle, why would it be that we could obtain a different sample mean if those two groups were sampled from the same population? Wouldn't we get the same mean if they were sampled from the same population? What would produce the difference in the sample mean?
Sampling variability, so we're just grabbing random
people we're going to end up with different things.
That's right. Yeah, just sampling variability. Do I have chalk? Yeah. Remember that one of the assumptions is that the population from which you're sampling, if that's the variable x, the population from which you're sampling has variability built into that population. Not everyone is identical. Not everyone has the same height. Not everyone has the same weight. Not everyone has the same blood pressure. And so if I randomly sample 6 people from this room and measure your blood pressure, and randomly sample another 6 people and measure the blood pressure of those 6 people and take an average, they won't be identical. Even if I give one group a placebo drug that has no effect, and measure those 2 groups' mean blood pressure, they're not going to be identical. That's not because the drug necessarily has an effect. It might be. It might also be due to the fact that I just happen to pick 6 people down here for one group and a more equal sampling for another group, just by random chance. Random sampling means I'm just picking out of a hat people from that distribution. And most of the time I'll pick people in this big lump, in the average. But occasionally, just through random chance, I'll pick someone with an extreme value. And so if that person happens to be put in the drug group, then there's a danger. I might incorrectly conclude, oh, the drug had an effect, whereas it was in fact just random sampling error that made their measurement different. So that's the logic of null hypothesis statistical testing, is assessing the probability of observing a difference in our samples that big if the null hypothesis was in fact true. So that's a t-test of 2 groups. And as you learned last term, an ANOVA is just like a t-test with more than 2 groups. N groups. So the null hypothesis is that all of the groups were sampled from populations that have the same mean, like the same population. And the alternate hypothesis, there's various ways of saying it, but one way of saying it is a bit cheeky. One way of saying the alternate hypothesis is simply that the null hypothesis is not true. The alternate hypothesis is not the null hypothesis. In other words, it's not true that the groups were sampled from populations with the same mean. So what that implies is one of the groups, at least one of the groups, was sampled from a population with a different mean than the other ones. You don't know which one, or which ones. So the p-value you get after an ANOVA assesses what's the probability of observing differences between group means as big as the ones that you observe in your samples if the null hypothesis were true. So here we have 3 samples of size 4, treatment 1, treatment 2, treatment 3, and those are the means of those 3 groups, 98.5, 8, and 3. What's the chance we could observe differences between those 3 groups as big as that if they were sampled from the same population? Is it a small probability? Is it a big probability? If it's a very small probability, then we would reject the null hypothesis and say, well, we're not that lucky or unlucky. That probably didn't happen, so the reason why they're different isn't due to sampling error, because that's really low probability. The reason why they're different must be due to the experimental treatment. And that's where you have to rely on your experimental design to be able to interpret that difference. If you did an experiment where the only thing that was different between those 3 groups that were randomly assigned was the drug they got, and you rejected the null hypothesis, then you can conclude those differences are due to your experimental manipulation. So ANOVA stands for analysis of variance. That's where the ANOVA comes from. And it's a test that compares the means of 2 or more groups. ANOVA has a lot of flavors, and we're going to see some of them in the course. Today we're going to start with single factor, one way, as it's called, between subjects and ANOVA. And so chapter 14 of our covers this. So one way between subjects and ANOVA is the starting point. The one way in that name means that there's one independent variable. Because as we'll see later in the course, you can have an ANOVA with multiple independent variables. We'll see two-factor ANOVA and n-factor ANOVA later. But one way means there's only one independent variable, like drug, and that would be placebo, drug 1, drug 2, drug 3. So one factor could have multiple levels, but there's just one factor. One thing is variable. And the between subjects part of it means that each participant in the experiment contributes an observation only in one group. So each participant only is a placebo, or only is drug 1, only is drug 2. In other words, the observations in those three groups are independent from each other. They're different participants. You could run an experiment where the same people get a placebo, and then later they get drug 1, and then later they get drug 2. That's certainly an experimental design you could do, but that's called a repeated measurement or within subjects in because each participant contributes a score to every level of the factor. And indeed, we'll see later, you can have a mixed ANOVA with some factors between subjects, some factors within subjects. And that gets a little bit ugly to look at, but it's possible. So today is about one way between subjects ANOVA, the simplest kind. So what ANOVA gives you, as you recall from last term, it gives you an F statistic. So t-test gives you a T, and ANOVA gives you an F. And the F statistic, as we saw, when was it? 2 weeks ago for multiple regressions. An F statistic is a ratio of two things, top and bottom. And for ANOVA, it's a ratio of two variances. The numerator is the between groups variance. That's the way of saying the differences between the groups. That's what those arrows refer to here. And the denominator is the within groups variance, the variability within each group. And so the omnibus F statistic, and omnibus means overall, the omnibus F statistic is a measure of how big the between group differences are relative to the within group variability. And so why is that a rational thing to compare? Well, here's two different scenarios. Here's a set of three groups, and I forget how many data points there are. 15 maybe. Here's three groups, and here's a different three groups. In both cases, they each have the same average value. So the orange ones here have the same mean as the orange ones here. The purple ones have the same mean as the purple ones, and the green have the same mean as the green ones here. The means are the same. So the difference between means of those three groups is the same in those two identical experiments. But what's very different is the within group variance. So on the left, the variance within each of these three groups is very small. Those dots cluster quite tightly around their means. Whereas here, the within group variances are very big. And so the F statistic compares those two kinds of variances. What's the ratio from between variance to the within variance? So for this scenario, the F statistic, that F ratio is going to be above 1. Right? If these two variances were equal, then the ratio would be 1. But here, the between groups differences are a lot bigger than the within groups differences. And so the top is going to be bigger than the bottom, and so we'll get a ratio above 1. For that scenario, it's probably true we would get a ratio below 1, because the variance within each group is actually bigger than the variance between each group. The difference between means of those two groups. So the top is going to be smaller than the bottom, and so we'll get an F ratio less than 1. So the bigger the F ratio, the bigger the F ratio, the bigger the differences between means are compared to the variability within each group. So why does it make sense to compute this? Like, if I just gave you those data, and I gave you those data, and I said, the orange is the placebo, and the purple and the green are two different drugs that I'm using to treat for, I don't know what, memory improvement. You take the drug before studying your exam, you get well, you get an A, well, I guess that's not a percentage. You get that many correct, or that many correct, or that many correct. So clearly, if I gave you those data, if someone gave you those data and said these are two drugs and that's a placebo, I would say, I would say there's pretty clear evidence that people that took this drug, they do a lot better. I mean, there isn't anybody in that group. I mean, everybody in that group is better than everybody in that group, right? They don't overlap at all. Whereas if you show me those data, I would be more circumspect. I would say, I guess if I squint, things are a little bit higher than those, but this guy that took this drug, he does worse than all of these people that took the placebo. And, likewise, these three people did worse than half of the placebo group. So does the drug really work? I don't know. So it's a bit harder to confidently conclude that. So the more variable the data are within each group, the less certain you can be about declaring that the group differences are not just due to random sampling error. Because this variance within group is kind of like a measure of the random sampling error. Does that make some sense? Okay. So the null hypothesis of the omnibus test is that the population means of all groups are equal. Not that the group means are equal. The population means from which the groups were sampled are equal. That's the hypothesis. Remember that point. The hypothesis of the statistical test is always about population. It's not about the sampling count. So the null hypothesis, each group is sampled from populations with the same mean. Now why do I do this? In an earlier version of the slides, I had it as each group was sampled from the same population. And then I changed it to each group was sampled from populations with the same mean. Anyone know why I decided to change that? Or how could those two scenarios be different? If there's multiple populations that have the same need, are they the same population? No, not necessarily, right? You can imagine a couple of scenarios. You can imagine one population like that has that mean, X1, and another population that has the same mean, but much smaller variance. Another population with the same mean, but a big skew to the right. So the characteristics of a population can be different than just the mean. In other words, you can have different shapes, different distributions that have the same mean that aren't identical. And so it is an important reminder that both the t-test and the f-test are a test of population means. They're not a test of populations being identical. So that's why I changed that. And the alternate hypothesis is that at least one group was sampled from a population with a different mean. At least one. Maybe more than one. And you don't know which ones. Not from the omnibus test. And the p-value you get from the omnibus test is the probability of observing an F ratio as big as the one that you got from your samples if the null hypothesis were true. So if the null hypothesis were true and the population means are actually identical, and you sampled n equals whatever for your different groups, and then you computed the means, and then you computed the variances, and then you computed an F, what's the chance you could have obtained an F as big as the one you did if actually the population means were the same? The probability is going to be above zero it's never going to be 0.0. There's always going to be some probability that could happen. How likely is it to happen kind of depends on the ratio of the within to between differences. In that scenario, I would say the probability is probably pretty high that you could obtain the difference in means that big. Whereas here, the probability is probably low that you could have obtained this scenario if the null hypothesis were true. You would have just happened to have randomly sampled one group over here, one group over here, and one group over here, right? I mean, it could happen, right? You could flip a coin and it could be heads 50 times in a row. It could happen, but it's probably unlikely. The more likely scenario is that those examples populations with different means. So this is just what I just said. Random sampling results in differences between your sample groups. It's just the nature of the beat. And the F statistic gives you an overall measure of the differences between groups as a whole. And under the null hypothesis, we expect the F statistic to be pretty close to 1 most of the time. But due to random sampling under the null, even sometimes it will be larger. And so the p-value gives us a measure of how likely it is to observe an F statistic as big as the one that we got if the null hypothesis is true.